So in the previous lecture we have talked about basics of equation of state. Okay, when you can expect departure from the classical gas law, we also talked about it. Then we introduced our formalism, general formalism for discussing the density of states. Thereafter we talked about occupation numbers, and then finally in the last class we calculated the energy density or kinetic energy density. Now in today's class let us start from after that. Okay, so what we are going to do now is we are going to talk about the calculations of pressure. Okay, now you see so basically when I am talking about calculation of pressure, this is basically the equation of state, right? Because equation of state means how the pressure depends on density, temperature, composition, that's it. Okay, so in order to obtain the equation of state or the pressure, we will need to have an expression just similar to the kinetic energy density derivation. Let us start with the derivation of very important theorem known as pressure integral, and we will use this result afterwards when we discuss about the calculations for classical gas, degenerate gas, radiation, and also at very high energies we will talk about electron-positron pair gas. So basically today we will talk about applications of pressure integral to 4 cases: classical gas, then degenerate gas, then radiation or photon gas, right? Photon gas, and then electron positron pairs gas which is made up of them. So 4 applications. So this is what I would like to talk about. Again, when I will talk about degenerate gas, we will be talking about completely degenerate gas, and there you will see that we will talk about non-relativistic case and also ultra-relativistic or extreme relativistic case, both of them. Now there is another part as well, which is the partially degenerate gas. Now that one I will not cover in today's lecture, maybe afterwards we will talk about it. So this is my plan for today. Okay, fine. So let's start with the derivation for pressure integral. Okay, now suppose we have particles in a box. Again, we always start with something that we are conversant with. So we start with putting particles inside a box, and let us consider the wall with its normal along the positive x direction. Okay, now the wall has a surface area A. So what is the pressure? The pressure will be simply force divided by area, right? And we can write pressure as dPdt. This is very basic. Okay, now let us consider, so let this be equation 25, continuing our previous day's equation nomenclature. Okay, now let us consider the simplest case where all particles move in plus x direction. Okay, Now they all have momenta p, okay, number density n. Now over a period of time dt, the particles within volume A Vp dt, okay, this is the volume. What will it be? They will basically collide. So internet was cut, anyway it's okay. So I was talking about that over a period of time dt, the particles within a volume, this much amount of volume, will collide with the surface. Okay, they will collide with surface. Now what is the total number of particles that will collide? Let's find it. Well, it is basically, you see, n into just this number, this volume, right? So this is equation 26. Now these particles will be bounced back with the same momentum after collision, but in the opposite direction. So the momentum change is 2p, right? Momentum change is 2p for each collision. Therefore, the total momentum change, therefore total momentum change, what is it? It is basically, we can write dp is equal to, you see, 2p into dn, right? So this is 2p into n a vp dt, equation 27. Okay, so far this is quite basic stuff. And so what about the force? Well, force is, as we know, dp dt. So this is just 2np a vp, equation 28. Now from equation 25, remember what was it? Basically the expression for pressure here. So if we use that from equation 25, we can have the pressure as F by A, and this is just 2np Vp. This is equation 29. Okay, now let us consider an isotropic particle distribution, right, where there is no preferential direction. So in that case, there will be an average 1/6 particle moving in positive x direction, right? Because if you consider the box here, you see, how many sides are there in the box? 6 sides, right? 6 sides. So if I am talking about the average of it, 1 2 3 4 5, and there is also another part over here. So if I am talking about isotropy, then there will be basically 1/6. So for isotropy, basically 1/6 of particles will be moving in this positive x direction. Okay, so as a result, you see, we can write P as 1/3 of NPVP. How does this 1/3 comes? You see, here. So this was the result. So I just divided it by 6, 1/6 of it, and as a result I am getting 2 by 6 equal to 1 by 3. Okay, so this is the last one was 29. So this is equation 30. Okay, now also you see the particles may have different momenta, not just p, and therefore what we need to do is we need to integrate over the momentum in distribution. Need to integrate over momenta distribution. So what will we have? So as a result we will have this result. You see, 1 by 3 p Vp Np dP. Equation 31. This is known as, this result is known as pressure integral. Okay, this is a very important expression for pressure. Now this is valid for all velocities, for all momentum distributions. Remember, as long as we have isotropic distribution. So this is valid for isotropic distribution. Okay. Any questions till now? This is quite straightforward thing. Okay. Now let's immediately see how we can get a relation between pressure and the kinetic energy density. Let's see. Well, let us start with the non-relativistic case. What happens? Well, in this case we have V is equal to P by M. Okay, and so as a result we can write P is equal to, you see, 0 to infinity 1 by 3 P, again P by M Np dP, and this is equal to again 0 to infinity 1 by 3. Now I can write it as P square by twice M, right here, not twice, just P square by M. So this is basically twice of Ek into Np dP, and as a result what I am having is basically 2 by 3 U. Okay, equation 32. So basically I am having, for non-relativistic case we are having this result, U is equal to kinetic energy density and pressure, they are related by this relation. What about ultra-relativistic case? Ultra-relativistic case. Now here we have V is approximately C. So let us again write P 0 to infinity 1 by 3 P C Np dP. Okay, now this is again equal to 1 by 3. Now Pc is just relativistic energy, Ek, then Np and dP. So this is 1 by 3 of U. So this means that for relativistic particles we have U is equal to thrice of P. Okay, so this is the relation. Now,
sir,
yes, this is valid for photons, right? Ultra relativistic case, remember this. Yes,
স্যার বলছি যে ইকুয়েশন অফ স্টেট যখন পড়িয়েছিলেন তখন ওই একটা ইকুয়েশন লিখেছিলেন জেনারেল ফর্মে P ইকুয়ালস টু ফাই রো P ডট রো P বাই রো এরকম কিছু একটা বটে। ওইখানে যে ফাইটা লিখেছিলেন নন রিলেটিভিস্টিকের ক্ষেত্রে 1/3 হয় আর ফাইটা
yes, very good, very good. Yes, yes, we have basically derived this relation. Very good point. Mane, this is a sort of relationship, but okay, this is a general sort of relationship. Same thing. 2 by 3 or 3 by 2. Same thing. That thing is we have just derived. Now it is very important to note that here these two relations, this one and this one, they are independent of the momentum distribution. Okay? Fine. I'm just telling you that this is valid in general. Now you must remember this relationship which we discussed in the last class, total density. This is basically equation 16, right? You must remember this, and also the relation that we have just discussed right now. We have basically derived the pressure integral. This one, P Vp Np dP. This is equation 31. Okay. Now you know that you should know that these two relations basically they allow us to calculate the pressure. So using these two, we can calculate pressure as function of number density for any gas made up of identical particles in local thermodynamic equilibrium. Okay. Now it is also important to remember that we have neglected in our discussion, what did we neglect? Basically the interaction energy between particles. That is, we have assumed that there are interactions between particles to establish thermal equilibrium, but they are weak enough to be neglected. Okay. Now this assumption is normally satisfied inside stars, and so we will follow this in our entire course. Okay. Now let us now apply this general formalism to derive the equation of state for classical gas. Okay. Fine. So we will be talking about Maxwell's distribution, classical gas. So this is the first application. Okay. Now in this case we have basically mc square much greater than E minus mu greater than kBt. Okay, equation 34. Now I am talking this in respect to the distribution functions that we discussed in the last class. So this means that particles are non-relativistic, and the exponential term in the denominator. Okay, so let me show you the occupation number which we discussed here. So the occupation number was this here, you see. Mu by kBt and plus minus 1, right? The plus sign was for fermions and a minus sign was for bosons. Okay, this we discussed in our last class. Okay, so what will happen this time? You see, in the denominator of this occupation function, this was basically equation 14. As a result of this condition, the denominator becomes very large. This means that the occupation number is much less than 1. So Fe is much less than 1, as a result of this thing for each quantum state. And also we can neglect this plus minus one term, so we can neglect, and this is very large. And as a result, we have the classical distribution for, so we have the classical distributions for bosons and fermions which are identical. Okay. So with this assumption or approximation, you can say, this approximation of equation 34, we have the classical gas distribution. Okay, তোমরা শুনতে পাচ্ছ তো? Okay, let me write it down. P by M, E is equal to mc square plus ek, and this is approximately equal to mc square plus p square by twice m. This is equation 35. Okay, now remember equation 15. Equation 15.
So density of state.
Yes.
Occupation.
Number density of particles. Let me again write it down. So equation 15 was basically the number density of particles with momentum between p and p plus dp, and we obtained it by multiplying the density of states with the occupation number, and we finally obtained this equation 15, which was gs into 4 pi p square dp by h cube into 1 by E minus mu by kBt plus minus 1. Okay. So this was equation 15. Fine. Now, because of this approximation, we have these equations, and as a result, this equation will now become gs again 4 pi p square dp by h cube, and here we have into multiplying by e to the power minus mc square plus p square by twice m minus mu by kbt. Okay, and we can write this as we can আচ্ছা এই যে দেখে নাও, আমি জাস্ট এই টার্মটা এখানে পুট করেছি, ই এর টার্মটা ওইখানে পুট করেছি, আর কিছু করিনি। ওকে, নাও এরপরে আমি যেটা করছি, সো আই এম জাস্ট রাইটিং দিস অ্যাজ a into p square, okay, a into p square dp into e to the power minus p square by twice m kBt. Okay, now this is equation 36. Okay, where we have collected all the constants together into a, and so basically a is gs into 4 pi by h cube into e to the power minus mc square minus mu again divided by kBt. Okay, this is 37. Okay, what about the number density of particles? Let me then write down. So number density of particles, so it is basically n is equal to 0 to infinity. Again we used this relationship just now in 2 or 3 slides back. So if we do that, we will have p square dp e to the power minus p square by twice m kbt, and this gives us a into twice m kbt to the power 3 by 2 holo, and this one here integral remains, and inside this we have dx into just a second, we have dx into x square into e to the power minus x, and this is equation 38. So what is x? Basically we have substituted this term, x square is equal to p square divided by twice m kbt. So we have made this substitution. Now you see this last integral, this has the value, this integral, if you estimate this, you will get that this value is pi to the power half divided by 4. So if we put this together, then we will have, you see, n is equal to, and putting again the value of a together, so we will have finally n is equal to 2 pi m kbt divided by h square here to the power 3 by 2, and here we have e to the power minus mc square minus mu by kbt. Okay, and this is equation 39. Now what does this equation tell us? Well, this equation also tells us how to derive the chemical potential mu once we know the temperature, after we know temperature and number density of the particles. Okay, this is important, you must remember this. Now similar to this total number density of particles, so this was number density of particles, we can derive the expression for the pressure as well, right, using the pressure integral. So this time let me write it down. I have already shown you how to write these results slowly, so I will be now moving little bit faster. Okay, and so I will be showing you the result. So you see, in a similar fashion you can derive the pressure, and this is equation 40, and here you see, similar to the last case, this last integral, its value is 3 pi to the power half divided by 8, and upon putting this value, okay, we will have, you see, this relation. Which is equation 41. Now, just now we have derived equation 39, right, number density. So what I am going to do, I am just going to divide equation 41 divided by equation 39, and upon doing that you will see that we will get this relation, or P is equal to N kBT, equation 42. So this is our equation of state for the classical gas or classical ideal gas law, right? Okay, now let us do some checking. And what is that? Which checking I am talking about? Basically, I would like to talk about the very first thing that we discussed today. The very first approximation that we started, which was equation 34. Here, let me again write down. So, let us check the approximation which we have used to derive this classical gas law, right? And what was the approximation? This was basically equation 34, which was our starting point. This was basically mc square much greater than E minus mu much greater than kBt. Now, what check do you want to talk about? You must be thinking, right? You will see, and it is very interesting how we will find the relationship. Basically, you see, we can use this relationship to find the distance between particles and compare them with the de Broglie wavelength. So, what we want to do is so basically we want to see what does this approximation physical meaning. Okay, we want to explore this. Now, as I was telling you, so basically you will see that this approximation requires the separation between particles to be much greater. So I will tell you that basically the physical meaning is that separation between particles, okay, will be much greater than typical de Broglie wavelength of the particle. So this is what we will show you. Let us see how it is so. Now, from equation 39, which was the number density expression, you see we have we can write, basically we have this relation. I've just written it a little bit differently. Now this is equation 43. Now in our approximation, which was this one, this approximation, the last exponential term of this equation is much smaller than 1, right? So this one is much smaller than 1. So this means that basically this thing, right? So আমি কি করলাম, তোমার এই যে using this approximation basically means that the exponential term is much smaller than 1. So here this term is much smaller than 1. So this means that n is much greater, less than this number, and let me define this number as nq, যেটাকে আমরা বলবো quantum concentration. Or critical number density. Also sometimes it is called critical number density. এখানে আমরা GS টাকে ইগনোর করেছি. We have ignored this since it is of the order of 1. So it has been ignored. Okay. Now notice that the term in the brackets here, the term within the brackets, is related to the de Broglie wavelength. Okay, let me show you. Now this is so because a particle has typical kinetic energy, you see, p square by twice m of the order of kBt. So from here we have P is of the order of 2m kBt to the power half, right? So the de Broglie wavelength of the particle is h by P equal to approximately h by twice m kb t to the power half. Equation 45. So this means that this approximation of this equation 44. So this means that there is approximation of equation 44 can be rewritten using, so rewriting equation 44, we can write this as, you see, this relation. This is this lambda. This is lambda d, de Broglie wavelength. Okay, this is just lambda d, de Broglie wavelength. Equation 46. Now, since the average separation, you see, the average separation between particles d is of the order of n to the power minus 1 by 3. So this above equation means that, so from these two we get d is much greater than lambda d. Okay, equation 47. So this means that the bolo
minus 130 লিখেছেন স্যার
number density. Now this means that the separation between particles must be larger than the de Broglie wavelength. Now you see, in quantum mechanics we have wave particle duality, and particles should be viewed as a sort of fuzzy ball having size of the order of de Broglie wavelength. When the separation is much larger than this size, the wave nature of the particles can be completely ignored. In other words, particles behave just like classical point particles, and hence they follow the classical Maxwell distribution. However, we must remember two very important points. And what are they? The first is that for photons, what about them? For photons, well, they never follow Maxwell distribution, because you see their chemical potential is equal to 0, and they always violate the classical condition, the number density, classical condition, also the relation we talked about previously. Another thing is that for light particles, you see the de Broglie wavelength is much larger, for them. So the critical density for quantum behavior is lower. So this means that the critical density NQ is lower for the light particles. Now when a star evolves, the density at the center usually becomes higher, and the lightest particles, electrons, are the first to reach the critical density, and therefore they are the first to exhibit the quantum behavior. In fact, you see, ions can also be approximated as an ideal gas in most regimes of interest. So, before I proceed forward with the case for electrons, how their behavior change when the quantum behavior manifests, let me first talk about very important point of mean molecular weight. It's a very important topic, and that will conclude the classical gas description, and after that we will talk about the degenerate gas. Okay. So, the next important topic is mean molecular weights. Now you see, so far we have only discussed the number density of particles n. But we still need to relate n to the density rho. Right? We have to relate this. Now this relation depends on the chemical composition of the gas. Now it is convenient, let us write this. Well, it is convenient if we write x as the fraction of as the fraction of mass in hydrogen, y as the fraction of mass in helium, and z as the fraction of mass of elements heavier than hydrogen and helium. Now these elements are normally sometimes called metals, although most of them are in fact carbon, nitrogen, oxygen, and so on. So because of this we have the relation x plus y plus z equal to 1. Right. Now let me just write this down again in a fresh paper. Just a second. Here. So we have this relation x plus y plus z equal to 1. This is equation 48. Now for a typical main sequence star, you see x is equal to 0.7, y is equal to 0.28 and z is equal to 0.02, and this is also valid for our sun. So you see, what does this mean? This means that most of the mass is in hydrogen and helium and very small fraction is in heavier elements. Now in most applications it is safe to assume that the stars are fully ionized. The only exceptions are stellar atmospheres. So the pressure is not only electrons but also ions. Now to use the ideal gas equation of state, we must count the number of particles in gas. Just a second. Okay. Now how do we do that? Well, so we have to count the number of particles. Now you see, we have to remember that each hydrogen atom has a mass of about mp. What about helium atom? Helium atom, it has a weight of about 4 times of mass of hydrogen atom. Okay. And heavier elements, element with nuclear charge Z, they have Z protons and approximately equal number of neutrons. Right. Therefore, each heavier element contributes a mass of approximately twice Z into mp. Okay. And the average charge of all heavier elements is what? Average charge? Average charge of heavier elements, basically you can say Z average is approximately 8. Now let us consider the number of atoms in a differential volume. So atoms in volume dV. You see the total mass will be mass is rho dV. Fine. And hence the mass of hydrogen, helium and heavier elements, what are they? Hydrogen x rho dV, helium y rho dV. ठीक है? This is hydrogen, this is helium, okay, and okay, and z dV, z into rho dV for heavier elements. Okay. Now in this amount of matter, hydrogen nuclei, how much are they there? Hydrogen nuclei is x rho dV divided by mp, this much hydrogen nuclei. And what is the number of helium nuclei? The number of helium nuclei is y rho dV divided by 4 times of mp. So this is number of nuclei. Okay, this row. And same for heavier elements, it is z rho dV divided by twice of z average. Okay. Therefore, now we can write down the total number of ions using this previous expression. So what is it? The total number of ions is therefore, you see, this number, equation 49. And what was 48? 48 is this expression. Okay, and we obtained this, and I am just putting this together over here to get equation 49. And so the number density, total number of ions, and then the number density of ions, it is, you see, basically given by this number here. Okay, dNi by dV. Upon doing this, we get this equation 50. Similarly, we can estimate the number density of electrons. So we have talked about ions. Now we can similarly talk about electrons. Note that a fully ionized hydrogen atom provides 1 electron per atom. A fully ionized helium atom provides how much? 1 electron per 2 nucleons. Okay, so if we talk about electrons now, so fully ionized H atom, it provides 1 electron per nucleon. Same fully ionized helium atom, it provides 1 electron per 2 nucleon, and so on. A heavier element with charge Z, it provides Z electrons per nucleus. Now in a typical case, we have A approximately equal to twice of Z nucleons, and so we get 1 electron per 1 electron per 2 nucleon, just like helium atom. Okay, so let me write down the number density of electrons. Fine. You see, the number density of electrons, it is then this number over here, which is equation 51. So the total number density of particles, what is it? That means ions plus electrons. It is basically given by this number. We have to add up the contributions for ions and electrons, and as a result You can check this by yourself as well. It is giving this result, equation 52. Now, it is convenient to define the mean molecular weight per particle. Again, mean molecular weight per electron and mean molecular weight per ion. So, let us do this. So, mean molecular weight. Let us define this, and I am writing down the expression over here. Okay, so mean molecular weight, I have given 3 definitions, right? So this is mean molecular weight per particle. This is mean molecular weight per electron, right? And this is again mean molecular weight per ion. Let me write the equation numbers 53, 54 and 55. Okay. Now it is important that we must not confuse the mean molecular weight with chemical potential, which is denoted by the same symbol. Okay. Okay. Now with this newly defined mean molecular weight, we may now write down the equation of state, right? So let us write it down here. So using this mean molecular weight concepts, we can write down the equation of states like this for electron, for ions. This is equation 56 and this is equation 57. So what about the total pressure? The total pressure, total gas pressure due to ions plus electrons, and this is basically written as this. You see, sometimes Kb by Mp is written as R, and then we can write P is so we can write also this relation P is equal to rho by mu T, rho R by mu into T. Sometimes we also write this. Okay, now this is equation 58 and this is the final gas pressure. So we did all this stuff to write this down in terms of the mean molecular weight, mu. Also note that the corresponding kinetic energy density, they are basically given by these values, which is equation 59. Okay. Now let me ask you a question using these definitions. So a question: can you calculate the mean molecular weight per particle, mean molecular weight per electron, and also the mean molecular per nucleon for Sun, where we know that for Sun X is equal to 0.7, Y is equal to 0.28 and Z is equal to 0.02. So I am giving you 5 minutes to calculate this and tell me what is the answer. Okay, I am waiting. So basically I am asking you to calculate per particle, electron, and this is ion. This is ion. Check these calculations. I am just giving you the result. I have waited. Okay, you will check that the values are mu is equal to 0.62, mu is equal to 1.18, and mu I is equal to 1.3. You check this. So this was question number 1. Let me give you another question. Very quick, short question. Now, this time I would like you to check whether the gas at the center of the sun is described as classical gas. So gas at center of sun, can we describe it as ideal gas? So let me give you the numbers. Rho C is equal to 1.5 at the center or core. These values kg per meter cube. Temperature is 1.6 into 10 to the power 7 Kelvin. Okay. Now you calculate this. How would you do? So basically I am asking you to calculate the critical number density and then check. 5 minutes. Write it down. So let me give you the answer. You can check it yourself. So you see, we have mu E is equal to 2 by 1 plus x. Okay. So this is approximately 1.2. So the number density of electrons Ne is equal to rho C divided by mu E into mp. This thing you calculate and you will find that this is 7.6 into 10 to the power 31 per meter cube. Okay. Now, what about the average separation between electrons? Well, this is again and this is equal to 2.4 into 10 to the power minus 11 meter. And this is what? This is less than Bohr radius. Okay. So the critical number density is NQ equal to 2 pi me kb Tc divided by h square, and this number comes out to be 1.4 into 10 to the power 32 per meter cube. Hence you see the actual number density of electrons at the center of the sun. Okay, which was it? The previous one here. Ne, how much is it? 7.6 10 to the power 31, whereas the critical number density is 1.4 10 to the power 32. So this means that the actual number density of electrons at the center of the sun is just below the critical value, right? Ne is less than NQ, and so as a result we can consider the gas at center of sun to be ideal gas. Okay. However, a rigorous treatment requires to account for the small but sometimes significant deviations from classical behavior. But I am not going to do that over here. Now, as the third question, but not basically question, and is example, third example. Let me talk about the early evolution of sun. You see, when a star just initiates the hydrogen nuclear burning, it is usually called a zero-age main sequence star. So a star when it just initiates H burning, it is known as ZAMS, Zero Age Main Sequence Star. Now, as an example, our Sun, it started out as a ZAM star. Now let us consider. So let us consider how the central density and temperature evolves as hydrogen is burned in the core of the Sun. Now you see, as hydrogen is converted to helium, the hydrogen, what happens? The hydrogen mass fraction X, it decreases, while the helium mass fraction, it increases. Okay? And from equation 53, this one over here, we can write, so from equation 53, we can therefore write and observe that the mu, mean molecular weight, it basically increases. Let me again show you. Here, this is twice x, this is 0.75y. So this one is decreasing much faster. So this one will increase. Okay. And so the central, and as a result of this, you see, the central pressure decreases if central temperature and density are kept constant. Okay, so in order for the pressure to balance the gravity, a star must contract. So this means star contracts. Fine. Now, what I am saying is that in order for the pressure to balance the gravity, so pressure balance gravity, so for that the star must contract to increase, and as a result there is an increase in density and temperature. Now as the temperature increases, you see, as temperature increases, the energy generation rate epsilon, due to nuclear reactions, it also increases, because this is highly dependent on temperature. In fact, energy generation is of the order of T to the power some factor, that I will talk about the details later on. Now these factors are different for hydrogen burning, helium burning, carbon burning, and so on and so forth. But remember that as the temperature increases, the energy generation rate due to nuclear reactions also increases, and more energy is transported. So more energy is transported to surface as well, throughout, but to surface as well. So in the HR diagram, the sun evolves from ZAM's position to the left, which means increasing temperature, and also up, which means increasing luminosity. Here, remember, we have a paradox, in the sense that as hydrogen fuel is consumed, the luminosity of sun actually increases. But this is a fact. Okay. So this is what a very basic HR diagram looks like, And from the very basic discussion over here regarding the evolution of sun from the Zam's position, so as the sun evolves in the Zam's position, so the movement is along this direction, along increasing luminosity as well as increasing temperature. Okay, this is what I was telling about.
ব্ল্যাক হোলের পজিশন কোথায় থাকবে?
ব্ল্যাক হোল, হোয়াই নিউট্রন ডোয়ার্ফ তো নিউট্রন স্টারও তো তুমি ভাবতে পারো। ওকে, সেটা কোথায় থাকবে? এবার ব্ল্যাক হোলের থেকে কি লাইট পাওয়া যায়? ডু ইউ অবজার্ভ এনিথিং? টেল মি।
Hawking radiation.
What is the temperature? How much luminosity are we talking about regarding Hawking radiation? Compared to the sun, if you see this plot, suppose this is a logarithmic plot, okay, this is a normal plot, linear plot, not logarithmic. Now tell me, where do you expect the black hole to be? Compared to the sun, this luminosity is very low, so it will be on this side. Again, the temperature, it varies depending on the mass of the black hole, right? So you can say more or less it is on the very low side over here somewhere. What about supernova? Supernova not only has the brightest luminosity but also temperature is high. So here, over there. Again, neutron star, it may have very high temperature but again very low luminosity. So neutron star will be on this region, and you cannot show this on this normal HR diagram because the values are very small, and in the log plot it will be going much below. Even planets. What about Earth? What about Earth in this HR diagram? Earth's temperature is not very high compared to that of sun, so it will be on this side. What about the luminosity? Well, it does not glow at all. It depends on what it gets from the sun, so very low luminosity. So Earth will be this side, Earth, and neutron star over on this side, black holes over this side, and supernova on that side. Okay, any more questions?
ব্ল্যাক হোলটা কোন জায়গায় বললেন?
এই যে ব্ল্যাক হোলটা এইরকম কোনো জায়গায় আছে, একদম নিচে। luminosity, temperature also very low. Here, over here, this side, very small black holes. What about us? আমরা কোথায় থাকবো বলো? হিউম্যান বিং আর মাচ লোয়ার। কিছুই টেম্পারেচার নেই আমাদের। কত টেম্পারেচার? বডি টেম্পারেচার very small in this axis. Again, কোনো luminosity নেই. So on this side, Earth's temperature is still higher than that of us. Okay, fine.